Good morning, everyone. So joining us today is Liang. Paul is a PhD student in the ML department at the CMU. So he studies machine learning foundations of multisensory intelligence to design practical AI systems that integrate them from and interact with a diverse range of real-world sensory modalities. So his work has been applied to many different domains, including robotics, affective computing, and healthcare. So I think his work can resonate with many of you here today. And on a personal note, I have known Paul for many years now. So I think about like 4 years. I always found his work super impressive, particularly in the area of multimodal AI. I think most of our research nowadays is pretty applied. So I found his work can give us a lot of theoretical insight into the foundation of multimodal AI. And I'm sure based on the title today, you're going to learn more about that. So I'm very excited to have Paul here today, and please welcome him.
Thank you. Hi, everyone. Thank you so much for coming. I'm really excited to come here today and present my latest research on the foundations of multisensory artificial intelligence. So we've seen great progress in AI. However, most of our best systems still only perceive a very narrow slice of the full multisensory world. For example, we have systems that understand our spoken words in language, but these systems don't also understand our vocal expressions, any facial gestures or body language we might be using to convey our expressions, such as pointing to a particular object. Similarly, we've seen great progress in AI for health. A lot of these systems are designed to capture data in a single modality, such as AI to process X-ray images in radiology. But wouldn't it be great if these systems could also understand other medical modalities as well, such as histology images under the microscope, medical sensors, or even things like wearable devices and smartphone data, which tells us a great deal of information about our daily health and well-being. So my research builds up both the machine learning foundations and also practical AI systems. It enables us to learn from a wide range of sensory modalities in the world. And to give a glimpse of the broad impact of my research, a lot of it has been applied to understand human communication, understanding humans and their intents through the words that they say, the vocal expressions they use, and the body language they use to express their behaviors. These systems can be very useful to understand sentiment and emotions, whether a person is happy or sad about a particular topic, and even whether people are being sarcastic or humorous about a particular topic. The industry has also been very interested in some of this research. So Meta, for example, exhibiting some of these AR and VR devices, are really interested in the problem of user satisfaction. Are users happy with this feature, or do they dislike this other feature? And again, that's something that they don't want to keep asking users in natural language, but they wish to sense non-invasively through any non-verbal expressions or sensors that might be collected in these features. We're also going a step further, looking at applications in mood and mental health. We've been working with psychiatrists at University of Pittsburgh, Columbia, University of Oregon, to look at teenagers at the risk of depression. Some of the teenagers have been diagnosed with depression, and some of these teenagers are at the risk of depression. And by looking at their smartphone data, which includes photos they're taking on these phones, different texts they're typing, and how they're typing it, we're able to make daily mood assessments on the mental health of these patients and relay this information back to these psychiatrists in their treatment. We also work with several medical schools. Working at Harvard Medical School, we've been looking at different indicators of cancer, looking at microscopic images of tumor cells under the microscope, looking at genomics data like DNA and RNA, and also other forms of biomarkers that are indicative of the types of cancers patients may have and the risk they may pass away from these cancers. And finally, I can't talk about multisensory without discussing robotics. We've been working with quite a few roboticists to build systems that are robust to imperfections in either modality. These robot arms, they have force sensors on them. And you can push these robot arms to simulate an earthquake, and the robot will rely on vision to solve the task. Likewise, they have a camera sensor, and if you start occluding some of these cameras with a folder to simulate rain or fog, the robot can rely on force to solve the task. So in this setting, different sensory modalities on these robots makes the robot more robust to imperfections in either modality. So underlying these applications are a set of core scientific contributions I made to the study of multisensory AI. That enables us to build systems that go from just language to language and images to a wide range of sensory modalities in the real world. And in this talk, I'm going to focus on two parts. In the first part, we're going to dive very deep into this problem of multimodal interactions. So in this setting, you have two modalities, X1 and X2, and there's some common label they want to predict given these two modalities. Now, this is a very general setup. It is a core building block of any multimodal problem, this problem of multimodal fusion. In this setting, we're going to study specifically the information provided by the modalities by themselves, overlapping between the modalities, and the information that emerges when we combine these modalities. We're going to show that by deeply studying this information, you can better understand your data and choose the right methods that work well for your data. In the second part of the talk, we're going to go broader. We're going to look at building systems that are able to take in many sensory modalities as input and make predictions on multiple tasks as input. So I call this a second generation of multisensory foundation models. We've already seen great progress in language-only foundation models that takes in language and makes different predictions for multiple tasks. But the future of these large language models are those that are going to be grounded in the real world. They can take in videos, sensor data, medical data, and more. So in that part of the talk, I'm going to highlight our early work in multimodal transformers, which have become the backbone of many of these large-scale multimodal models today, and also our recent data engineering efforts in scaling some of these models up to more input modalities and output tasks. And finally, I want to highlight that a lot of this has been done for the real-world impact. It's been worked, at least work that's been applied in understanding the affective states of humans in healthcare and robotics, and also in education. And as we build these systems for the real world, it's very important to understand not just systems that are well-performing, but systems that are able to ensure the fairness, safety, and privacy of user data. So I've done some work in this direction, and I hope to continue some of these efforts moving forwards in building more safe multimodal AI. So in the first part, we're going to dive deep into the foundations of multimodal interactions. At a very intuitive level, multimodal interactions describe how modalities combine to form information relevant for some task. And I'm going to use these Venn diagrams to show these modalities. Modality 1, X1 in red, and modality 2, X2 in blue. And in the most general case, these Venn diagrams contain some overlapping information, because you can think sometimes you have captions describing parts of the image, but at the same time, these modalities can also have some unique information. Not everything in the image is going to be described within the caption. And finally, I'm going to use a third random variable, Y, to represent the task you're trying to predict. This might be making a classification given image and text. Might be predicting diseases given medical image and medical text, and so on. Any task that you're trying to predict given these two modalities. And at a high level, there's three important interactions that we care about. The first interaction is that of redundancy, where both modalities contain some overlapping information that is relevant to the task. So think, saying something positive like this movie is great with a huge smile on your face. Both of these indicate that the person really liked the movie, and together you're very confident that this person loved the movie. So that's an example of redundancy. A second important interaction is that of uniqueness. There's unique information present in one modality, relevant for the task, but that information isn't present in the other one. So think saying something slightly positive, like this movie does a good job developing the characters, but with mostly neutral facial expressions. So out of this, language provides the information for the task, and that information is unique to language, not present in your verbal or visual expressions. And the third type of interaction is that of synergy, where the information isn't present in either of these modalities to begin with, but only emerges when you fuse these modalities together. And one example I like to give is someone saying the word wow with angry or frustrated expressions. You have a positive word with negative expressions together, and only together you can get a sense that a person is actually being sarcastic about a particular topic. So again, that's an example where sarcasm isn't present in either modality, but only emerges when you fuse these modalities together. Now, these interactions are quite intuitive, and in fact, they've inspired a long line of work in multimodal learning. And one particular interaction I want to highlight that has inspired a lot of work is that of redundancy. There's been a long line of work aiming to capture redundancy. So starting from early works in code training, for example, that trains a classifier in one modality and uses that to pseudo-label data in the other modality, essentially keeping classifiers that only agree in how they predict on either modality. As well as recent work such as multimodal contrastive learning that takes in images and the paired captions of these images from the internet and aims to learn embeddings for these that they're very similar together and very far apart for images and incorrect captions. And also recent work such as multimodal language models like GPT-4. These models take in images, generate some embeddings for that, and use that to generate captions or answer questions about these images. A lot of these methods are designed to capture redundancy. That there is some shared information between these modalities, and it is the shared information that I care about in capturing. So what can go wrong? What if you take a method designed to capture redundancy, a particular type of interaction, and apply it to other types of interactions? For example, in settings where there's unique information, in settings where there's synergistic information, or even in settings in health, where even domain experts don't know what interaction might exist between your modalities, and it is a question of scientific discovery. Well, these methods will fail. Over here, I'm showing a very simple example of taking contrastive learning, a method designed for learning redundancy between your modalities. When there's a lot of redundancy in your data, they work really well, 98% performance. And as you slowly start increasing the amount of other interactions and increase the amount of redundancy, these methods slowly start decreasing in performance to as low as 30%, very close to random. And that's just one problem in a long list of problems that we have in multimodal learning today. We don't have answers to basic questions, such as if I have a multimodal data set, what is the right model to use? Similarly, why is it that sometimes I spend so much time and effort training multimodal models, but yet it doesn't even outperform a very simple baseline using only a single modality? So a lot of these questions can be answered if we have a deeper, more fundamental understanding of these multimodal interactions. And therefore, in the first part of the talk, I want to highlight 3 important questions that are very fundamental to the field. Firstly, can I actually understand what interactions are in my data? If I have a multimodal data set, is it primarily redundant information that I care about? Is it more unique in either modality? Or is there some synergy between the modalities that I aim to capture? Secondly, what interactions do our models actually learn? And if I can answer both of those questions, then I can answer this holy grail. What models are most suitable for my data, both in practice and also provably? So these are very long-term questions, and I'm going to show some of our recent progress towards answering some of these questions. So in the first part of the talk, I'm going to first start by giving you some background in information theory. Information theory is going to be a very natural perspective to quantify and formalize some of these kinds of information that I've talked about. In the second part, we're going to dive into some of our main contributions in estimating some of these information theoretic quantities in practice, especially on large-scale real-world data sets. And we're going to show that how, by estimating these interactions, you can better understand your data and you can choose the right method that works well in practice on your data. And finally, we're going to discuss some of the broader applications to deploy some of these methods in, including in mental health and in pathology. So to begin, a mathematical framework for multimodal interactions. So the setup is that you have some joint distribution P over your 2 modalities, x1, x2, and your label 1. And together, these 2 modalities give some total information towards predicting y. This total information can be broken down into each of these 4 parts. How much redundant information there is, how much unique information there is in either modality, and how much synergy there is, where information only arises when you fuse these modalities together. And our goal is to break down this total information into each of these 4 parts. Now, there's 2 key ideas that enables us to do this decomposition. The first key idea is that if you have a joint distribution P over x1, x2, and y, there's 2 other important distributions that you can infer. We call these distributions your unimodal marginals. So those are distributions P of x1 and y, so marginalizing x2 away, and a distribution P of x2 and y, so marginalizing x1 away. Now, these 2 unimodal marginals are very important because redundancy and uniqueness are encoded within these marginals, but synergy is not. So to see that, we had our first example for redundancy. You were saying something positive in language, x1 to y was positive, and you were showing something positive in your gestures, x2 to y is positive. So just from x1 to y being positive and x2 to y being positive, from these marginals, you have the sense that there is redundancy in your data. In a second case, you're showing something positive in language, and you're showing something neutral in your expressions. x1 to y is positive, x2 to y is neutral. Again, just from these 2 marginals, you get the sense that there is uniqueness in your data. But this fails for synergy. You're showing something positive in language, but you're showing angry expressions that were negative. Without knowing the true y, given both x1 and x2, you're not able to distinguish whether it's uniqueness or synergy. If the true y is positive, then it's unique information in the first modality contributing to the label. If the true y is negative, that's unique information in the second modality contributing to the label. And if the true y is something completely different, such as sarcasm, then that is synergy between those 2 modalities. So that's the first idea. You can infer these unimodal marginals, and redundancy and uniqueness are encoded within these marginals, but synergy is not. That also means that if you have these marginals, you can couple them together to form new multimodal distributions that has the same amount of redundancy and uniqueness, but a very different amount of synergy. So again, the first example, x1 to y was positive, x2 to y was positive. From those two marginals, you could create a multimodal distribution that given x1 and x2 is still positive. And because that's the same as the original distribution that you started with, that means all of the redundancy contributed to the information, and there's non-synergy in your data. In the second example, you saw that x1 was positive, x2 was neutral. You created a multimodal distribution with given x1 and x2 is positive. And because that's the same distribution as what you started with, that means all uniqueness contributed to the information, and there was no synergy in your data. In the third case, x1 was positive, x2 was negative. You can try to create a multimodal distribution with given x1 and x2. It's either positive or negative. But that's very different from the true distribution P, which indicates that a person was actually being sarcastic. That means you're losing a lot of information by considering the coupling of these two marginals, and the information that you lost was the synergy in your data. So to see that more formally, what we did is that we started from a joint distribution P over x1, x2, your modalities, and your label y. We inferred a marginal over x1 and y, and we inferred a marginal over x2 and y. And we then consider all of these intermediate distributions Q, again over x1, x2, and y, where Q satisfied a coupling of these unimodal marginals. And by coupling, I mean that Q of x1 and y is equal to Q of x1 and y, and Q of x2 and y is equal to Q of x2 and y. Making sure Q satisfies these couplings keeps the same amount of redundant and unique information because redundancy and uniqueness are encoded within these couplings. And that means you can find the Q, distribution Q within the set of Qs that is the least total information. That keeps the redundancy and uniqueness the same, but minimizes the synergy to 0. We know that P, the distribution you started with, had redundancy, uniqueness, and synergy, which means that the difference between these two terms is the amount of synergy in your distribution. And in fact, you can prove this. You can show that the Q star that minimizes this quantity, that is the least total information, is exactly a distribution with 0 synergy. Because if you apply the definition of synergy to Q star, you get S of Q star equals I of Q star minus the minimization over Q, which gives you back I of Q star. Those two terms cancel out, and you get 0. So now we have a formal mathematical definition of synergy. And the question then is that, can we estimate this definition in practice? So there's two terms here. Our first term is the mutual information term. And in fact, estimating mutual information is a relatively well-studied problem in machine learning and statistics. And we have ways to approximate the first term in practice. So then we're going to focus more on the second term. How do we minimize mutual information in the presence of these couplings? That's a relatively new problem in machine learning. Yes? So P is the orbital distribution. So P can be the true orbital distribution. In practice, you might observe P hats, which are samples of the original distribution. And Q are the distributions that you estimate, which are 0 synergy. So I can help you how much synergy that is. So in fact, later on, when I talk about the estimators, you're going to see that in practice, of course, not going to assume you have access to the true P. In distribution form, I value a sample from P, but you can still estimate the theoretical terms approximately. So we're estimating times. Right. Right. We're going to focus on the second term because this approximation problem of estimating Q, there's the least information with respect to the couplings is a relatively new problem. For the first term, just estimating information in P, there are standard ways to do it in machine learning. So it's mutual information estimation. Sure. So our goal is to estimate the second quantity. So in the first estimator, we first highlight that finding a distribution that has the least mutual information is equivalent to finding the distribution that has the highest entropy. So mutual information and entropy are just inverses of each other. So the goal is to find this distribution Q within your set of couplings. So Q of x1 is equal to P of x1 and y, Q of x2 and y is equal to P of x2 and y. Finding a Q within this set of couplings that has the highest entropy, that where you're the worst in predicting y, given your two modalities. So in fact, this problem is very simple. If x1, x2, your modalities and your label are small and discrete in support, this is actually a convex optimization problem with linear constraints. Right? Because entropy is a concave function and you're maximizing a concave function. So this can actually be solved exactly if x1, x2, and y are small and discrete in support. So see what that might look like in practice. Assume we have two modalities, text and images, and assume that these modalities are ones where you have good feature extractor score. So text may be through language models, images through pre-trained vision models. And this is assume that these embeddings are good enough that you're comfortable clustering. So one of 4 embeddings for text and one of 3 embeddings for images. In which case, this problem of finding out synergy is the same as learning the diffusion Q. And it's very simple support. One of 4 choices in x1, one of 3 choices in x2, and one of 2 choices, assuming y is final. So that's your optimization variable Q. You have to make sure that Q respects these constraints. So that means that summing over the columns, you get something that matches the row margin, P of x1 and 1, and summing over the rows, you get something that matches the column margins, P of x2 and 1. So ensuring these marginals are the same keeps the same amount of redundancy and uniqueness in this distribution. We're also making sure that Q is not negative and its entry is sum to 1. So that's the optimization variable Q. You can plug Q into any convex solver because maximizing entropy of Q is a convex problem, and that returns you the Q star that has the highest entropy while respecting these constraints. And that Q star is the one that has 0 synergy in that distribution, which means you can compute how much synergy there is by taking the difference with the original distribution P. And we actually show that if you have synergy, you can infer all the other interactions immediately as well. So that's the first estimator. The second estimator is more suitable for settings where your modalities are not small and discrete in support, which happens in many natural settings. Let's say you have high-dimensional data that's continuous in nature, videos from sensors, and so on. Now this problem now becomes more challenging because you can't even write out Q, right? You can't even write down the distribution Q because there's an infinite support over your possible videos and infinite support over your possible sensors. So instead of solving Q exactly, we're going to solve it approximately. We're going to define a Q tilde. These are again joint distributions over x1, x2, and y. But instead of over the full distribution, we're only going to define it over a batch of samples. So this Q tilde is only defined as a joint distribution over maybe 4 videos that you see and 4 sensors that you see. So this matrix will be 4 by 4. So in fact, every ij entry in this Q tilde matrix essentially tells you the joint likelihood of the I video in your batch with the j sensor in your batch, and for a particular one. And again, assuming y is small and binary, for example. So this Q tilde can be learned by neural networks, right? Q tilde can be learned by extracting features from videos, by extracting features from sensors, and taking an outer product between them. So that turns something that is 4 by dimension and 4 by dimension into a 4 by 4 matrix. So that gives you a way to parameterize these approximate distributions Q tilde over a small batch of videos and sensors. Now, again, a main part is to make sure this Q tilde still respects your constraints, that it falls within this set of unimodal marginals. But that can be done very easily. That can be done using a synchronous algorithm, which is a differentiable algorithm that rescales your rows of your matrix to follow some desired row marginal, P of x1 and y, and rescales the column of your matrix to follow some desired column marginal, P of x2 and y. So again, this makes sure that Q tilde has the same marginals, which means that it has the same redundant and unique information. We can then plug this Q tilde into your max entropy objective. So this will maximize the entropy of Q tilde and find a Q tilde star that has the highest entropy while respecting these constraints. And that is a distribution which has 0 synergy, which means you can compute how much synergy there is and also how much of other interactions there are. Now, the key idea here is that this optimization problem is differentiable, maximizing the entropy. Respecting the constraints on matrix normalizations, that's differentiable. Creating a matrix Q tilde is all differentiable. That means you can train all of this end to end. And you can take this objective, plug it into your favorite solver like stochastic gradient descent, PyTorch, and train all of this end to end to find a Q tilde star with 0 synergy. And one thing I want to highlight are that these estimators are very efficient, right? The first estimator was based on callback optimization. It solves in a matter of milliseconds. Even this estimator just approximately solves it by sampling batches of videos and sensors and another batch of videos and sensors. You can solve these problems very quickly, more than 100 times faster than training any multimodal model to begin with. That means it's always worth it doing this to understand the interactions in your data before informing what model you should be using for your data. So to see some of these results in practice, I'm going to show two examples. In the first example, your first modality is spoken language. And your second modality is all nonverbal expressions outside of language. So that includes visual expressions, facial gestures, and also vocal expressions like shouting or laughter. And the goal is to understand the sentiment of the users within these videos. So by running these estimators, we find that there is a lot of unique information in language. That is a predominant modality. And that makes sense because we say happy things and we say positive things. But the second most important interaction is that of redundancy. That means we do say positive things while showing positive gestures, and we say negative things while showing negative gestures. So in fact, a lot of this evaluation was done by humans, right? We actually got humans to look at these videos, to label all the interactions they were using. The humans were perceiving the sentiment of the speakers. And because of this pattern of interactions, we can suggest using a model that is language only to capture most of the performance. Or if you want to use a multimodal model, you should use something that forces the agreement between both modalities because there's so much redundancy in your data. Second example I want to highlight is again using the same two modalities, spoken language in the first one and everything that is nonverbal in the second modality. And the goal is to understand whether people are being sarcastic in the video. And again, we find that language is the most important interaction because sometimes we do say sarcastic things. But the second most important interaction is that of synergy. So there are actually many practical examples in the world where you are saying something positive but showing negative or angry expressions. And you have to synergistically combine these modalities. And we can propose using a multimodal transformer model to capture these synergistic interactions in your data. Yes?
So are these graphs showing visual information for two different data sets, one of which is set of examples, one of which is smart language? Or are you showing something about particular visual information that each of these particular examples would respect?
Oh, we're showing for the whole data set. So we're not doing point-wise, we're just doing general visual information. We're using the estimators that we just talked about.
But the two partition the data set somehow into examples that seem to be that set of examples that seem to be sarcastic.
Well, these are two separate data sets. So this is a data set collected for sarcasm. All the labels are just happy, sad.
And they have to both have the same modalities.
Right. Most of these data sets are all supported on the same human communicated modalities, but they're separate data sets and how to select them. Okay. Sure. And because of the synergy, we can propose using a multimodal transformer to capture these synergistic interactions. I'll cover this model in more detail in the second part of the talk. And again, just give a little bit more context about model selection. We can actually use this method to choose between many different multimodal models. Models that use only a single modality in either one. Models that are based on contrastive learning, models that are based on multiplicative interactions, and even other forms of higher order interactions like transformers. And in fact, using our method to first understand the interactions and choose the model most suitable for learning those interactions, you can, in one shot, select models with more than 96% of performance as if you had tried all of these models on your data set. And that gives you a good prior in informing you what models you should be using based on the interactions that you discover in your data. And finally, to wrap up the first part of the talk, I want to highlight some of the real-world applications we did using some of these frameworks. The first application is that of mental health. The goal is to look at these patients at a risk of depression, and they've given us access to the data, the text that they're typing on their phones, and also the way they were typing, what applications they were using, and their speed of typing these words on the phone. And the context was to understand the daily mood of these patients so that we can help these psychiatrists in treating these patients at the risk of depression. Over here that we find there's a unique information in either modality, but there's actually a lot of redundancy and synergy. And this manifests in certain words that may seem positive in nature, like love, thanks, and haha. When these words were typed very quickly, it's a sign of very positive mood. But when these words were typed slowly, with deliberation, that was actually a big sign of negative mood. Likewise, some negative words, like don't and just, if they're typed very quickly, can be a sign of negative mood, but if they're typed slowly, it's a sign of neutral mood. So it's important to contextualize what words were being typed and also the pattern of how they were typed on these phones. And because many of these interactions are quite idiosyncratic, some people use more photos, some people took more text, did more typing, and so on. We ended up training a global model, which learns information from multiple individuals in the study. This leverages the power of scale and learns person-independent features, and also personalized local models. So these models were actually able to be trained on the smartphone, were very quickly adaptable to how these individuals use particular modalities on their phone. Some of them more tailored towards photos, some of them more tailored towards text and typing, and so on. The other added benefit is that now these local personalized models, because they're trained directly on the phone, also allows you to not leak the data from these personal phones onto a centralized server, which keeps some notion of privacy. And together, these models gave quite accurate and personalized mood markers that are currently used by psychiatrists to continue tracking these patients who are at risk of depression. A second example I want to highlight was that in pathology, we've been looking at medical images. These are microscopic images of tumor cells and also genomics data. By looking at these together, we can make better predictions on the risk of these patients. And we find that for different cancers, different interactions are actually more important. For glioma, for example, this type of brain cancer, a lot of unique information is genomics was important. On the other hand, for pancreatic cancer, there was a lot of synergy. There was a predominant interaction that our estimators returned. And these insights were useful because now they were explainable to doctors why in certain cases multimodal helped. And in the case of pancreatic cancer, because of all this synergy, multimodal gave more than 12% improvements over individual unimodal models. Whereas for cases like glioma, in brain cancer, training multimodal models didn't really give any performance improvement over just glioma unimodal models. And to summarize the first part of our talk, we looked at very in-depth this problem of multimodal interactions. So there's two modalities and a task they're trying to predict. This is a core building block for almost any multimodal problem. We look very in-depth at understanding the information these two modalities can provide, how to estimate this information, and how do you use that to choose the right methods in practice. In the second part, we're going to go broader. We're going to look at building these multisensory and multitask foundation models. They're able to take in many input modalities and make predictions of many tasks. Think these large language models grounded in many modalities in the real world. And the second part, we're going to highlight two main contributions. Our first contribution is the fact that many of these real-world modalities have a temporal nature. So you don't just have X1, X2, your two modalities, but you have X1 across time and you have X2 across time. Right? Think saying many words across time is showing many non-verbal expressions across time. Which makes the problem that we talked about in the first part of the talk more challenging, right? Because now we have to learn these multimodal interactions, even though they might not be exactly paired up at the same point in time. So we're going to discuss some of our early work in building multimodal transformer architectures. They essentially learns all these pairwise interactions between different words in the sequence with different non-verbal expressions in the sequence, even though they may not be at the same point in time. And finally, I'm going to wrap up the talk by showing our recent efforts in scaling some of these multimodal transformers up to many more input modalities and many more prediction tasks, essentially creating a foundation for multisensory AI in the future. So first up, multimodal transformers. So in this setting, as we mentioned, you have multiple elements across time. You have first modality, such as 3 words across time, and multiple gestures across time, 4 gestures across time. And the key idea of these multimodal transformers is to learn this cross-modal attention matrix. In this case, it will be 3 by 4, telling me how every one of my 3 words should interact with every one of my 4 nonverbal gestures. So these cross-modal attention matrices are learned using an outer product, taking XL, my data for the first modality, passing it through some trainable transformation, WL, taking an outer product with XV, my data in my second modality, with some trainable parameters, WV. So this outer product, again, turns something that is 3 by dimension and 4 by dimension to 3 by 4. I'm going to apply a normalization by square root of D, because every one of these entries in a 3 by 4 matrix is a d-dimensional by d-dimensional vector product. So that magnitude scales very quickly with D. We're going to renormalize by square root of D, so the variance goes back down by 1 over D. Yes?
So this is sort of cross-extension.
Yes, cross-extension applied to multiple modalities. And finally, we'll apply a softmax. A softmax essentially turns every entry in this row into something that is non-zero, non-negative, and sums to 1. You can actually interpret these as attention weights. For example, the word definitely takes the interaction of 0.5 with laughter and 0.5 with eye rolling, non-negative and sums to 1. And likewise, the word enjoy, we see an interaction of 1 to laughter and 0 everywhere else. Non-negative and sums to 1. And finally, this cross-modal attention matrix can be multiplied with your actual non-verbal gestures, the actual features for laughter and features for eye rolling, to give you a new embedding. But embedding that is not just language only, but is language interacting with these non-verbal expressions. You're actually taking a word, definitely taking a 0.5 interaction with your eye rolling features and a 0.5 interaction with your laughter features. And there's several key ideas here, right? First of all, this attention is bidirectional. We saw how we can use this cross-modal attention to learn a new language feature interacting with vision. If you multiply it the other way, you get a new visual representation interacting with language. It's also learning redundancy and synergy. Each of the attention weights can be learning redundant interactions, for example, enjoy with laughter, both indicating positive, and also synergy, for example, definitely an eye rolling, indicating that a person is actually being sarcastic. But we saw 3 interactions, right? We also saw uniqueness. How do you learn uniqueness? You can learn that using self-attention. So that wouldn't be 2 different modalities doing cross-modal attention with each other, but rather the same language and the same language, learning a 3x3 matrix, learning how each of the 3 words interacts with each of these 3 other words. So that learns unique information. So together that learns all the interactions that we need across these 2 modalities. And finally, these are very efficient because you're essentially doing matrix multiplications and normalizations. You can parallelize this over multiple GPUs to learn all interactions between pairwise elements at the same time. So to see how these methods work, some important baselines are with those that are pre-aligned, methods that only look at the word interacting with visual gestures at the same point in time. But of course, those methods struggle because if your words are not happening with the exact same time as your nonverbal expressions, you're not going to learn this pairwise information. A second common type of method, or baseline, would be those that are based on forced alignment, for example, CPC, connectionist temporal classification. So these traditional methods of alignment look at the word carefully, learn what nonverbal expression it should be aligned to, for example, laughter, and remove both of these elements and recurse on the rest of the sequence. So these methods learn attention patterns that are monotonic. Whereas cross-modal attention is flexible because now you can learn attention patterns with the same word interacting with features before in time and also features afterwards in time. So we started doing a lot of these for video tasks, like understanding motions, sarcasm in videos, and they gave large gains of 5 to 10% over multiple tasks. But nowadays, they've also been broadly applied. They've been applied to settings of taking image and text. Image, treating large images as a sequence of patches, treating text as a sequence of words, and using multimodal transformers to learn pairwise interactions between different image regions and different words in your sentence. And you can start pre-training these across multiple tasks like question answering, summarization, or you can attach a language model at the end and use that as a backbone for these vision language models. They also been used broadly in other multimodal applications. I want to highlight an application in medical they've been working on. We have these large microscopic images, large, very high-resolution images under the microscope, which are more than 10,000 by 10,000. We're going to break that down into 256 or 256 patches. We'll look at these genomics data, which are DNA and RNA. You can treat that as a sequence of tokens. And essentially, these multimodal transformers allows you to learn the pairwise interaction between different individual local patches in the image with different genomes in the sequence. And that allows you to predict different types of risk and disease in patients. In the case of cancer, for example, these models were actually reasonably interpretable because you could look at which pairwise interactions the model emphasized in making a prediction. And over here, I'm showing one example. So this EMT genome was highlighted by the model that actually a genome known in biology to be indicative of the aggressiveness of tumor cells. And in fact, this model has both highlighted that genome and also highlighted the regions of tumor cells that are actually daily with hypotheses. That's an example of an interaction that the model has learned using multimodal transformers. And finally, to end the talk, because all of these methods, these multimodal transformers are so broadly applicable to different input modalities, we decided to scale these up. In fact, you can treat the whole world as a partially observed multimodal problem. And sometimes we see language and speech when communicating with humans. We see language and images when we see images and sensors when doing robotics. Can we train one model across all of these partially observed input modalities that we see across the world? And one recipe of doing that is despite all these modalities being very different, at a first order approximation, you can treat them as some form of input sequence. You can see images as sequences of patches, text as a sequence of words, sensors as a sequence of time series, and so on. You can apply modality-specific embedding. This identifies that language appears in one task and languages will appear in this other task. Applying unimodal transformers, so this learns unique information, how words in your sentence interact with other words in your sentence in the same modality. Applying multimodal transformer, this learns pairwise interactions between words in your sentence and images. That's unique, redundant, and synergistic interactions. And also training task-specific classifiers for many different tasks at the same time. And by training all of this together, you can end up with one model architecture with one set of parameters across all of these different input modalities and output tasks, leveraging the power of scale. So to see how these methods work, a common baseline is to just use methods that are specialized, specific to a certain input modality and specific to a particular prediction task. And over here, we're essentially showing all combinations of these specialized models. With x-axis being efficiency, how much parameters are used, so smaller is better on the right, and y showing performance, average performance across all of these tasks, higher is better. And in blue are essentially more than 10,000 combinations of these specialized models for different modalities and tasks, with red being the Pareto frontier. And we can start by training one model. We call this high MMT, high modality, multimodal transformer. And because this model is multitask in nature, you're immediately saving a lot of parameters. Right? You're not duplicating parameters used for all of these different tasks. You're saving a lot of parameters, as many parameters as you have number of tasks. But the performance is just average. The performance lies within the realm of these very specialized models. Now we've seen two extremes. We've seen extremes where you're specializing everything, and we've also seen an extreme where you're sharing everything. A natural question to ask is, what is the right amount of modality and task-specific processing? And we find that a useful heuristic is to actually quantify which modalities are similar with each other and enable us to share parameters. So that can be done using training a model on one modality and seeing how well that model transfers to other modalities. Ones that it transfers well to should be similar modalities, should use the same parameters, and ones that it doesn't transfer well to should be very different modalities and use different set of parameters. So that informs you how much unimodal parameter sharing to do. And likewise, for the fusion, if you have two modalities that are interacting in a certain way when you're fusing them together, how well does that same interaction process transfer to other pairs of modalities? For the ones that it transfers well to, you should be using the same set of multimodal parameters, and ones that it doesn't transfer well to should be using a separate set of multimodal parameters. So in practice, it's quite efficient. We're essentially saying, if I have a pre-trained model, for example, a pre-trained language model, how does the same language model transfer to code, to images, to genomics data, and so on? And we apply that in practice, we find that there are actually certain groups of parameters, modalities that transfer well to each other. The first group are more temporal modalities. Some of these large language models do transfer well to speech data, we like sensor data, which also has a temporal pattern across time. A second group are more spatial modalities. So models trained on visual gestures can also transfer to images on multimedia, on the internet, and medical images. Data with more spatial nature. Modalities that are more structured, such as tables and sets, where there are elements within these modalities, so there's computation invariance within these elements that transfer well to each other. On the multimodal side, we find that vision and language and vision and speech actually fuse very similarly. So you can use the same set of parameters, but otherwise there's a lot more heterogeneity in how these modalities interact than the modalities themselves. And finally, that completes the curve. We have these heterogeneity-aware transformer models. By designing the right amount of parameter sharing, you get a lot more efficiency, because you're still sharing more parameters than specialized models, but you get much better performance. You recover the best performance of these really specialized methods. And some examples we show the most improvement were in those robotics, sensor, dynamics robots, vision, tasks, and also HCI, which have a user interface of mobile screenshots. Again, these are examples where you don't have that much data in those modalities to begin with, but by sharing parameters with other modalities, you're learning better, more general information about these tasks. So to summarize, in the first part, we look very in depth at this problem of multimodal interactions. This basic building block of having two modalities and a task that is common to many multimodal problems. By understanding the information and choosing the right methods in the principal way, we show how we can make these methods more explainable and usable by practitioners. In the second part, we looked at broader scope. We looked at building these multisensory foundation models that are able to take in many input modalities and make predictions on multiple tasks at the same time. And we saw these multimodal transformer architectures, and also our recent efforts for scaling some of these up to more input modalities and prediction tasks. And therefore, we see both ends of the spectrum, methods that are really specialized, looking at deeply understanding the information, and also methods that are leveraging the power of scale. And one summary is that multimodal and multisensory is still very difficult. We've barely scratched the surface of some of these fundamental questions in multimodal learning. And we've barely scratched the surface of how many input modalities these models could eventually take in practice. And therefore, I'm very excited for some future directions. One short-term future direction is building these multisensory models, but building them with a foundation in mind. For example, building systems that are able to take in tabular data and sensors as modalities. These are two common modalities, very important for the real world, in the medical space, in the sensor space. But yet, deep learning doesn't really work well for these modalities. We've been doing some really recent work in collecting benchmarks for IoT sensors, and also combining traditional time series methods suitable for these sensors with deep learning methods. We've also been working on this problem of dynamic modalities. In a lot of the settings that I talked about today, the modalities were given to you and fixed. You iterated on the method. But many real-world settings have this question, where I have collected some modalities, and which other modalities should I start sensing next? Right, so that requires us to understand the benefits of modalities through the performance they can give, but also contextualize the costs, such as risks of using more parameters, having more training time, and collecting more modalities. And finally, questions concerning the safety, ethics, and alignment. You've already seen chances where LLMs will be unfair or unsafe. That's just one modality. But as we start equipping these models with the capability to process images or generate images, there are more sources of bias that may happen. So we're building some ways to make sure these LLMs are more safe, but also how we make sure these multimodal models that we train are safe and aligned. A lot of things I've talked about today were in perception, taking in modalities and making a prediction. The future will be methods that are also able to reason and take actions in some embodied world. And recently, I've been working on some of these agents that are able to work on the internet. Agents that are able to look at the earphone, decide what you want to buy, choose the right one based on price, check out, and enter your shipping address to actually send it to you. And these kind of agents are able to help in a lot of productive tasks, such as online shopping, and also in the future, perhaps in Microsoft Office and Excel. So there are some challenges here, building agents for the virtual world, and also if you're building agents for the real world, robots are able to perceive sensors in the real world. Building methods that are not just making a prediction, but able to search and plan, able to look at how the actions influence the world and observe what new multimodal observations may see in the world. And also building systems where modalities are used not just in the input space, but in the action space. For example, systems that can use actuators, tools, and APIs. And finally, in the long run, my long-term goal is to build systems that are able to help humans with multisensory well-being. We're going to collect more and more sensory indicators about ourselves, about our physical health, about our physiological health, and also about our social and emotional wellness. For example, our daily mood, our social interactions with other people. How can we build AI agents that are able to assist humans towards improving various aspects of wellness? For example, when humans want to get higher quality sleep, better mood, or more productive in the workplace. So again, several challenges here. Building systems that are able to perceive social, emotional, and medical indicators, and collaborating closely with medical experts in doing so. Building systems that are not just AI by itself, but are very closely intertwined with humans that closely interact with humans. And finally, making sure these systems are not just general purpose systems across the average of everybody, but are extremely personalized while retaining the privacy of user data. And that's all, folks. Thank you for listening. I'd love to take any questions about my current research and also future missions. Thank you. Yeah. Thanks.
implicit argument that these notions are somewhat universal information or universal for each of the modalities. But I think at this believe the estimate means the estimations are based on the presentations and not on each of the modalities.
Right.
So the overall histograms that you're showing, I would assume that those histograms would be different. For the same data, the same modality, the histogram would be different. If you're building the estimation space on a different representation. So that would create lots of variability. Each one of the how much synergy, for example, here between the two models. And that would create some hurdles for kind of completely
That's a good question. So a couple answers to that question. The first answer is that, yes, you're right in saying that these estimators in practice require to extract some features first, because it's impossible to just look at raw data and measure, for example, some of these distributional quantities. So that is true. But in fact, in our experiments, we found that these estimators are quite robust to the feature extractor that you use. As long as they are a unimodal feature extractor, that's good enough. You're extracting general features of text or images. In fact, what will be the most ideal is unimodal feature extractors like PCA, they literally only compress a unimodality by themselves. What can go wrong is if you start using feature extractors that will train in a multimodal way. Let's say you start using a clip feature extractor to get image embeddings or text embeddings, then that will be biased because clip was trained to only keep the redundant information and discard everything else. So that would give you a biased view of what interactions are actually present in the data to be done. Yeah.
But imagine, for example, for encoding text, I'm just using, let's say,
right.
Kind of changing the scale of that this model after speaking with you guys seeing the changes about.
Right.
Are you arguing that by changing the scale of the scale impact these
so we've not looked at scale, specifically language models, but we looked at one-hot embeddings, type of words, word embeddings, BERT models, and so on, and we found that it was quite robust to these. In fact, what is important here is not just X1 by itself, but X1 and Y. If I look at, for example, the information that is kept about the label. So in some sense, I wouldn't say there would be a big difference if you start using more large models. In fact, yes, we just will improve in quality. And a lot of how we evaluated this was twofold. Settings where you remove this potentially confounding variable, so looking at data that were just like binary bits, or even simple cases which were lower dimensional, where you could exactly estimate these quantities, in which cases estimators recovered the exact quantities. And for real world data sets, we got humans to annotate what is interacting with. Because humans can't perceive when I'm speaking, whether it's redundant or unique or synergistic. So that was in some sense a ground truth. So forming a concrete ground truth was important, in which case you could then benchmark against this actual ground truth. Okay.
That is the benefit to multimodal data. Wondering if you kind of explain the you essentially have a model that takes all this data and comes out with a single label. How obscure these flow that.
Right, great question. So therefore, I presented two spectrums, right? One spectrum, we're using purely data-driven methods. We're leveraging the power of scale, and we had models that took in more and more modalities and made more and more prediction tasks. But the other hand, we also have methods like this, where it's explainable in a sense because you're exactly trying to understand what interaction the data contain and why exactly you chose a particular method to learn that type of interaction. So you're actually making the whole modeling process more transparent in this other end of the spectrum. And one other example I want to highlight is that, in fact, some of this has also inspired, and we've done some subsequent work in building ways to visualize what your models have learned. I just want to share one key idea is that if you have a model that takes in language and images, for example, you make some prediction of, for example, emotion. People have done like this first order data to understand how language, which words of language is most influential in making a prediction. And that can be done in the first order data. The second order data, what that tells you is that were used by the model to make that prediction. So we're here starting with sad and sine interacting with the lip movement going down as the person was saying those words. So as we have more and more multimodal systems, there are also possibilities to build systems that are able to visualize and explain specific multimodal workings of these systems, which is an active area, something that I do as well.
Sure. So you've talked sort of abstractly about different modalities. In the answers to some of the questions, you mentioned particular models have clinic. But I wonder if you could talk a little bit about modalities that don't have well-established encoders yet.
So that's something I'm very excited about. In fact, recently we've been building some of these, well, starting with benchmarks first, because we need benchmarks first, then have IoT sensors. Right? I think that is definitely the next frontier of multimodal. We have image text multimodal, but the next generation is going to be those that are able to take in different sensory modalities about it. So when I say sensors, I mean heat sensors, to detect what type of object you're working with, depth sensors, proprioception sensors, and tactile sensors, which are very common in robotics. That tells you the position and also how far you're away you are from solving the task. So you recently created some of these benchmarks, and naturally, these kind of methods, they don't have good encoders, right? You have more traditional methods based on time series analysis and sensor fusion, and we also make them more compatible with some of these large-scale models that are present in deep learning. So that's an active area of research.
So what is different between time series sensor data and time series language data?
Well, the continuous nature is a big issue, right? They don't come in the form of nice discrete tokens. So doing mass language modeling and doing a soft natural tokens is still reasonable. If you want to do this continuous sensing, regression, self-supervised masking regression, that's going to be a big issue because you're not going to learn finite fine-grained features in the continuous space. The other issue is just that there's so much noise. And the fact that you let these sensing different devices, it will be quite different. You have more distribution chips.
I'm not sure that there are more distribution chips in sensor data than language. In language, you often change topic.
Right. So I think maybe noise. Yeah, noise is going to be one application because these are very continuous data is very easy to introduce noise into the products.
You also mentioned tabular data.
Yes, tabular data as well. So like tabular data is an example where I think the best methods are still like decision trees and gradient boosting. So how do you make those models, the tabular data, compatible with, for example, large language models in a language? Let's say you have a class that requires both language and tabular data. That's something I'm trying to say.
Okay, I'm meeting with you.
Okay. Yeah.
A sense of this efficiency of this information estimator, like yeah, really right that I still thought that it was quite hard, right? High dimensions.
Right.
And in the sense of like the error margins, like is this like quantity that was easier to estimate?
That's a good question. So we didn't study exactly the sample complexity, at least in theory. Like we're actually proving a sample complexity, but in practice, these estimates are quite stable. And the biggest reason is that when you look at these estimators, we want to estimate these estimators, it's not often that we want to know that redundancy is 0.3 bits or 0.31 bits. It's most often which interaction was the most important. Right? Is this data set primarily synergistic or is it primarily redundant? So in fact, the order of these interactions never really changed, regardless of the sample complexity, or if you start using different encoders or introducing different noise into the data. So it's mostly about the right. And when I say order is the most important, what I mean is that to give a little bit more context about how we subsequently use these estimators to choose the right methods, we're going to start by generating a bunch of these synthetic data sets. So some data sets are purely synergistic, some data sets are purely redundant. You can generate a ton of synthetic data sets with respect to some interaction. And the goal is that if you have a real data set, you're going to find the nearest synthetic data set in interaction space. And by finding the nearest synthetic data set, you're going to return the model that works the best for that nearest synthetic data set, which can be pre-computed. And that actually allows you very quickly to choose the right method for your real world data set because there is some similar nature. For what does work well, and the actions because of the real set. That's why the order of interaction is what matters the most, rather than the specific value of the interactions. Therefore, I guess it's one way of quantifying the performance, when you could in one shot select models that were 96% of the performance, as if you had just tried all of these methods on your real world data set.
All right, so, okay, thanks for that.